I'm going to be working on the homework solutions for 8.2, but there were still a couple of problems from 8.1 that I had not completed that I said I would complete. So let me get to those first. Now, what we're kind of relying on here for these problems is this theorem that I did in class that said every bounded monotonic sequence converges. So if someone gives us a sequence, if we can show it's bounded and we can show it's monotonic, then the conclusion is that it converges. It doesn't tell us what it converges to, but it does tell us that we have convergence. So we're going to look at number 37. The sequence is 1 over 2n plus 3. Now we know that this converges. I mean, there's no question about this, because if we let n go to infinity, it's pretty obvious that we're going to get 0. What I'd like for us to do, though, is get used to the idea of how to show something is bounded and how it's monotonic. So the instructions say, determine whether it is increasing or decreasing or not monotonic at all, and then is the sequence bounded. So although we know it converges already, I'm going to just practice showing these two things. So first of all, what do we think it's doing? As far as the monotonic is concerned, is it increasing or is it decreasing? And it could be doing neither one, but okay, that's what checking for the monotonic means. It's going to be this one or possibly neither one. So let's just look at the sequence. If I plug in 1, I get 1/5. I plug in 2, let's see, I get 1/7. Plug in 3, I get 6, 9, 1/9, and so on and so forth. So it looks like these are getting smaller as I go, which means that it appears to me that it's decreasing. So that's what I want to try and show. I want to show a sub n is decreasing. To show that it's decreasing, I need to show that a sub n is greater than a sub n plus 1. Right? That's the definition of decreasing. The nth term of the sequence, whatever dot that is on our plot of this, it's going to be higher than the one next to it. So as long as that continues to happen, we know that this sequence decreases. So I've got to show that inequality. All right? If I can show that this is true, then I'm done. So what I'm going to do is I'm going to first show, what is a sub n? Well, a sub n is just that expression, 1 over 2n plus 3. I want to show that that's bigger than a sub n plus 1. So that's this same sequence right here, but replacing that n with n plus 1. So I would get 1 over 2, replace the n with n plus 1, then plus 3. Now let me try and convince you that this is always true. So what I'll do is I'll distribute the 2 through here. 2n and then plus 2 and then plus 3 is plus 5. So I think I could probably convince you right here that it's true because this number is bigger than this number. We kind of knew that already here, but just watch as I go through this. Let me show you how I can definitively convince you that this is true. So what I'll do now is I'll kind of like cross multiply. I'm going to multiply this side times 2n plus 5. At the same time, I'm going to multiply this side by 2n plus 5. That will clear out this fraction over here. I don't have to worry about flipping the inequality over because this is guaranteed to be a positive number, right? Because n is positive. And then at the same time, I'm going to multiply both sides by 2n plus 3. 2n plus 3. And that will cancel the fraction out on the left side. So I get this and this cancel. I get this and this cancel. And so I'm left with 2n plus 5 times 1, which is 2n plus 5, is greater than, and then over here I'm just left with 2n plus 3. Now I'll just subtract 2n on both sides. They just happen to cancel, and I get the inequality 5 is greater than 3. And the question is, we were saying, is this true? If this is true, then it's decreasing. And we plugged things in, and we got this as a conclusion. Well, this is always true. Always true. So I'll say true for all n. Okay? 5 is always greater than 3 no matter what. So what I've shown is that it's decreasing. Okay, now the next thing to do is to show it's bounded. So to show it's bounded, I have to show that the sequence of numbers always stays between two numbers. It's always, these numbers are always bigger than something, and they're always smaller than something. So what does it seem like is reasonable here? So for bounded, I want to show that my sequence, a sub n, is stuck between two numbers, something and something. If I can show that, then I can say it's bounded. I think the obvious choice for what it's greater than is 0, right? Because all these are positive numbers. And let me put in this right here. That's our sequence. But what is that always smaller than? Well, I think that all of these are going to be fractions, right? 1's always going to be on top. They're going to get smaller. So 1 would be a natural choice. So let's just check to see that this is true. First of all, checking that one. If we multiply both sides by 2n plus 3, right? So I'm doing two separate problems here. I'm trying to show this is true first. Multiply both sides by 2n plus 3. It goes away here, and 0 times 2n plus 3 is 0. So I get 0 is less than 1. That checks, okay? That's always true. Now what I want to show is that 1 over 2n plus 3 is less than 1. So I'll multiply both sides by 2n plus 3. I'll get 1 is less than 2n plus 3. And now what I'll do is I will subtract 3 from both sides and get negative 2 less than 2n. And I'll divide both sides by 2 to get negative 1 is less than n. So this will be true as long as n is bigger than negative 1. But remember, n always starts at 1, then 2, then 3. So this is going to check also because it's a sequence and we start at n equals 1. So this is good to go. So what we've shown is that this sequence is bounded, right? So we've shown it's monotonic, we've shown it's bounded, and therefore it must converge, even though we already knew that to begin with. Okay? But that's how you do it. So what's most important here is the actual technique, the method, because the problems get a little more challenging. So let's look at the next one. So for 38, we have 2n minus 3 over 3m plus 4. And let's work on the monotonic part first, all right? So let's try and take a guess as to what we think is happening here. And to do that, we might have to write out some of these. So if n is 1, let's see what I get. n is 1, I get negative 1 on top. And then if n is 1 on the bottom, I get 7. And then if I do n is 2 on top, I get 1. And on the bottom, 2, 60, we get 10. And then the next one, if n is 3, 6 minus 3 is 3. On the bottom, we get 13. So if we continue this pattern, it's going to be 5 over 16, then 7 over 19. 19. So if we look at this, can we tell what's happening with this sequence? Is it getting bigger or smaller? Well, it looks like we're starting out, if we were to graph this, if we plug in 1, we're at negative 1/7. We plug in 2, we're at 1/10. We plug in 3, we're at 3 over 13, which is actually bigger than 1/10. or is it 3/13, 1/10? How do you compare these to see, without a calculator, how do you compare 1/10 and 3/13? Well, you get a common denominator. So 130, so I multiply 13 on top and bottom here. And then here I multiply top and bottom by 10. And so with the common denominator, these two rewritten, you can tell that 30 130ths is bigger than 13 130ths. So yes, this number, 3/13 is bigger than 1/10. And then let me check 5/16. If I were to compare 3/13 to 5/16, then what we could do, we got a common denominator here, a faster way of doing it, okay, to check which side is bigger, is to multiply this times this. So 16 times 3, that's 30, it's 48. And then you do this times this, and that's 50, 65. And since this times this side is bigger number than this side, this fraction is bigger. So I know that this is bigger than this, so it's a little bit above. And this keeps happening, okay? That's what it looks like is going on. So it looks like my sequence is increasing. So that's what I'm going to try and show. So I want to show that a sub n is increasing, getting bigger as I go. All right, well, then what I need to show is that a sub n is less than a sub n plus 1. This is opposite of what we showed last time. So I want to show this. So what is a sub n? It's 2n minus 3 over 3n plus 4. Is that less than, now a sub n plus 1 is 2 times n plus 1 minus 3 over, and now we have 3 times n plus 1 plus 4. So writing a sub n down, and then replacing a sub n, or n with n plus 1. Let me kind of clean up a little bit here. 2n minus 3 over 3n plus 4. Is that less than, let's see, 2n plus 2 minus 1, so 2n minus 3, which is minus 1. And then 3n, let's see, plus 3 plus 4 is plus 7. Okay, so is that true? Well, this one's not as obvious, all right? You might say, okay, look, the denominator here is bigger than the denominator here, right? This is bigger than this, so that means this should be smaller, but at the same time, these two are not the same, so this one's smaller than this one, so this should be bigger. So it's hard to just look and tell, so what I'm going to try and do is convince you by just algebraically working with this. So I'll multiply both sides by 3n plus 7. That'll clear out this. And then I'll multiply both sides by 3n plus 4. And that'll clear out this. And so what I'll get is this times this. So 3n plus 7 times 2n minus 3 is less than, over here, this times this. So 2n minus 1 times 3n plus 4. So I need to see if that's true. So let me go ahead and just multiply this all out. I get 6n squared. I get minus 9n. I get plus 14n. And then I get minus 21. Is that less than 6n squared plus 8n minus 3n minus 4. I need this to be true in order to say that this is increasing. So right away I notice I have 6n squared on both sides, so I can subtract it on both sides, it's gone. Negative 9n and 14n, that's 5n minus 21. Is that less than, let's see, 8n minus 3n is 5n again, right? 5n again, and then minus 4. Notice I have 5n on both sides, so I subtract it, it's gone. Get negative 21 is less than negative 4. Is that true? Yes, that's true always. So since that's true always, this thing is always increasing. So we are good to go. It is an increasing function, or increasing sequence. Now I need to show it's bounded. So what do you think you can squeeze this between. What would you squeeze that between? Well, we can kind of cheat a little bit. We could have just figured in the very beginning, we could have said, you know, what, does this converge or diverge? And you could have done, oh, okay, it's like L'Hopital, infinity over infinity, and you would have found out that it converges to 2/3. But sometimes it's not that easy, so we have to just look at the sequence and see if we can figure something out. Looks like the smallest number we ever get is -1/7. So I think it's safe to say that we think this is always greater than -1. And then we always think it's probably less than, let's see. These numbers don't ever appear to be bigger than 1, right? If we look at the rest of them we had, we always had the denominator was bigger than the numerator. So probably less than 1. If I can show this, right? I want to show that this is true, then I would show that it's a bounded sequence. So let me start with this left side. Is -1 less than 2n minus 3 over 3n plus 4? All right, well, I'll multiply both sides by 3n plus 4. And when I distribute through, I get -3n minus 4. Over here, all that's left is 2n minus 3. And let me get all my n's on one side. So I'll add 3n, I'll get 5n. And then I'll add 3 to both sides, and I'll get -1. And then -1 divided by 5 is less than n. Is n always bigger than -1/5? Yes, because it's a sequence. So this side checks out. Now let's check this side. Is 2n minus 3 over 3n plus 4 less than 1? Well, again, multiply both sides by 3n plus 4. You'll get 2n minus 3 is less than 1 times that is just this. Move all my n's over, so I'll have 1n on the right side when I subtract 2n. I'll subtract 4, I'll get -7. Is n always bigger than -7? Absolutely. So this checks. Therefore, it's a bounded sequence, it's monotonic, and therefore it converges. All right, let's look at the next one. n -1 to the n, or 39. n -1 to the n. All right, let's try and get an idea of what's happening here. If I write some things down here. If I plug in 1, I get -1. If I plug in 2, that's 2. -1 squared is +1, so I get 2. And then if I plug in 3, I get 3, but then -1 cubed is -1, so -3. And then 4, and then -5, and then 6, and then -7. This continues. And if I look at this on a graph, a plot of the sequence, I've got at 1, I'm at -1. At 2, I'm at +2. At 3, I'm at -3. At 4, I'm at +4. And so what's happening is this is flipping back and forth between positives and negatives, but it's fanning out. It's getting bigger and bigger. So there's no way that this could be an increasing sequence. It doesn't keep going up. It doesn't keep going down. It's going back and forth. And on top of that, it doesn't appear to be bounded, right? There's no number that I can pick that will be a ceiling or a floor for this that'll always be between, that our sequence will always be between those. I can't say infinity. Infinity is not a number. It has to be a number that it's fixed between. So just by inspection, this is not monotonic, and this is not bounded. All right, number 40. N plus 1 over n. All right, so let's take a look at this. Let's try and get a feel for what's happening here. If I plug in 1, get 1 plus 1 over 1, that's going to be 2. If I plug in 2, I'm going to get 2 plus a half If I plug in 3, I'm going to get 3 plus a third. 4 plus a fourth, and so on and so forth. This is really 2, and then if we get a common denominator here, we'll have 4 over 2 plus 1 over 2, it's 5 over 2. Here, if I get a common denominator, I get 9 over 3 plus 1, that's 10 over 3. Here, 4, we get a common denominator, 16 plus 1, 17 over 4, and so on and so forth. So what's happening if I actually plot this, if I plug in 1, I get 2. If I plug in 2, let's see, what's this? 2.5, it's bigger. 3, if I plug in 3, I get what? That's 3.3, something like that. So I'm going up. 4, I'm getting what? 4.25 or something like that. So it appears that the further I go out, the bigger it gets. Now I could confirm that by taking the limit as n goes to infinity. If I do that, that goes to infinity, that goes to 0, so this goes to infinity plus 0, which is infinity. So this thing is definitely not bounded. And as far as monotonic, well, is it always going up? It looks like it's always going up. Let's show it though. We have to actually show whether or not it's monotonic or not. So for monotonic, I want to show, I think it's increasing. A sub n is increasing just by looking up there. So I want to show that a sub n is less than a sub n plus 1. So let's try that inequality. I'm going to continue it over here. Okay, so I'm trying to show this. So I'm trying to show that n plus 1 over n is less than, when I plug in n plus 1, it's n plus 1 plus 1 over n plus 1. So that's what I'm trying to show. So let's see. Right now, I don't have to clear fractions right now, because what I can do is I can just subtract n on both sides. And then I can do, let's see, 1 over n less than 1 plus 1 over n plus 1. Why don't we move this to the other side? 1 over n minus 1 over n plus 1 less than 1. Is that true? Well, let's get a common denominator between these two. So you have to do an n plus 1 here, n plus 1 here. You have to do an n here and an n here. So what you'll get is n plus 1 times 1, which is n plus 1. Then you'll subtract n, and you'll put that all over the common denominator, which is n times n plus 1. Is that less than 1? So cancel those out, and what you get is 1 over n times n plus 1 is less than 1. I think we can convince ourselves that this is true right here, because the smallest n could ever be would be 1. And if I plug 1 in here, I'm going to get 1 times 2, that's 1/2. 1/2 is less than 1. And then as the bottom gets bigger, this gets smaller, so it's definitely going to be less than 1. But let me try and take it one more step. I'm going to multiply both sides by n times n plus 1. So it'll clear out on the left, it'll appear on the right. So I get 1 is less than n times n plus 1. And then I'll distribute through. And I think that's pretty obvious. Again, the smallest n could be would be 1. And in that case, I get 2 is bigger than 1. And then if you plug in 2, obviously that's bigger than 1. So I think at this point, I'm really convinced that that's true. So this is an increasing sequence, but it is not bounded, all right? It is not bounded. It might be worth it for me to show you how you could show it's not bounded. So what I'm going to do is I'm going to contradict myself here. I'm going to act like it's bounded, all right? Bounded above. So is a sub n bounded? looking at that sequence, can I say it's bounded below? I can say it's bounded below because 0 is definitely less than 1 n. It's 1 over n. Because this right here is always a positive number, plus this is always a positive number. Definitely this is true, all right? You could go through and get a common denominator right here and put n squared plus 1 over n. You could multiply both sides by n and get zeros less than n squared plus 1, and then you would say, yeah, that's obviously true. So it's definitely bounded below. Is it bounded above? Because you have to have both conditions for you to say it's bounded. So is it bounded above? Let me show how you would contradict yourself if you think it is. So suppose that you think that n plus 1 over n is less than some upper bound, all right? Then that would mean getting a common denominator here. N squared plus 1 over n is less than capital M, right? And in this case, n squared plus 1 is less than m times n. So check this out. If we pick n to be 1, then what happens? Remember, m is a fixed number, right? M is a fixed number. So if m is a fixed number, then let's let n be 1, and let's see if this is true. Well, 1 squared. 1 squared plus 1 is 2 is less than m than m. Well, okay, that's not bad. I mean, that's okay. That looks like if you choose your m to be big enough, then you can definitely make it bigger than the first guy, right? If I pick an m big enough. But let me show you how this would fail, all right? What if I choose my n to actually be equal to the capital M? Whatever you think the top bound is, I'm going to come in here and I'm going to use that as my n. Then this right here becomes m squared plus 1 is less than m times n, which is m squared. And then what happens is these two cancel. You get 1 is less than 0, and you've contradicted yourself. You've said, hey, look, I think that this is always less than some m. You can't change that. That's stuck now. And you say, all right, well, if that's true, then this has to be true. And then you come over and you say, oh, well, if n is 1, sure, it works. But if I go out far enough in my sequence, I will actually be able to come up with a contradiction of the inequality, which means that it must go the other way, and it must be bigger, so it's unbounded. That's just to show you how you could prove to yourself that it was not bounded above. All right, that's it for 8.1. Let's get into 8.2 now. You know what, I think I might just make this its own video. It's what, it's almost 30 minutes? Yeah, I'll make that its own video.